All right, once again, 5.5, multiple angles and product to sum. Multiple angles is when you've got 2 theta for an argument. Product to sum is where the initial expression is a product, and then the second one is a sum, or vice versa. So the task is to use double angle, power reducing, and half angle identities to evaluate and solve trigonometric equations and expressions. So here are the families of double angle identities, which are the first ones we're going to consider. And one thing to note is, although there's only one identity for sine of 2 theta and tangent of 2 theta, there are 3 for cosine of 2 theta, and sometimes one of these would be advantageous over another. So let's say sine of theta is going to use a double angle identity at some point. So sine of theta is 3/4 on this interval, so that's Q1. Everybody see why that's Q1? You guys kind of suck at radians in the unit circle, so make sure you understand why that's quadrant 1. We're going to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So first of all, sine of 2 theta, so we'll use the identity from the previous page, 2 sine theta cosine theta. So in order to use this identity, I need cosine, and the quickest way to find cosine here would be to use a reference triangle. I've tried to apply identities to almost every problem, but it's just so much more efficient to do this. If the sine, in other words, the ratio of the opposite to the hypotenuse is 3 to 4, then we need to find this unknown side. We'll call it b, using the Pythagorean theorem. So 3 squared plus b squared equals 4 squared. 9 plus b squared equals 16. Subtract 9 from both sides. B squared equals 7, and b equals the square root of 7. So that means the cosine, and we're in Q1, so I know the cosine's positive. Cosine of theta is radical 7 over 4. So now I can say this is 2 times 3/4 times radical 7 over 4. So 2 times 3 is 6 on the square root of 7 over 16, which would reduce to 3 on the square root of 7 over 8. So that's our sine of 2 theta. We created a reference triangle for theta, and then we plugged in the resulting trigonometric ratios for sine and cosine into the formula that describes the sine of 2 theta, because that's one of our tasks here. That one's now accomplished. Let's find cosine of 2 theta. And remember that we've got our choice of 3 identities in the case of cosine. So let's just use the one that's easiest in our case. 2 cosine squared theta minus 1. And that's easy because we know the cosine here. So 2 times radical 7 over 4 squared minus 1. So that's 2 times 7 over 16 minus 1. Remember PEMDAS, we have to find that exponent's value before we do any multiplication. And so that's 14 over 16 minus 1. And so that's negative 2 over 16, or negative 1/8. Stop me if you have any questions. Just applying identities is all we've done here. If I had chosen one of the other cosine double angle identities, the answer would have been the same. So we got one more task, and that is the tangent of 2 theta. So let's see here. Once again, we'll check out those IDs. I see the tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. And I can find tangent theta by the reference triangle. So that's 3 over the square root of 7. We don't have to worry about rationalization because we've got this expression to plug it into, and we'll just rationalize at the end if needed. So you would normally turn that into 3 on the square root of 7 over 7, but we won't bother in this case again because we're just immediately plugging it in here. And then 1 minus 3 over the square root of 7 squared. So that's 6 over the square root of 7 over 1 minus 9 over 7. 6 over the square root of 7 over, this is 7 over 7, so negative 2 over 7. Remember that when we divide by a fraction, we can keep, change, flip. And then I get negative 42 over 2 on the square root of 7. So that's negative 21 over the square root of 7. Here's where I'll rationalize. Negative 21 on the square root of 7 over 7. I'm going to reduce again now, because 21 is divisible by 7 3 times. Negative 3 on the square root of 7 is our answer. And remember, the same rules don't apply to tangent as do the other trig ratios. The other trig ratios have to be between negative 1 and positive 1, including the bounds. Sine and cosine do. But for the tangent, the range is all real numbers, so it can be anything. Remember how I told you in chapter 4 you can use the hinge theorem to kind of parse your answers? Smallest angle across from the smallest side and so on. Another way to parse your answers in trigonometry is to make sure your sines and cosines are between negative 1 and 1 for their output. If you get an output of 3, for example, you screwed up. If you get an output of negative 3, also screwed up. But for the tangent, it can be anything. All right. Questions about this one? Should be pretty straightforward. Okay, I think we're good to go on that. Let's solve an equation using a double angle identity. So we notice here, we've got a problem. Different arguments increase the complexity of an equation by several orders of magnitude. So if I have different arguments for the trig functions, it becomes extremely complicated to solve them. And in this case, it requires the application of one of these cosine identities. But one and only one of these makes sense in this case. So you see I've got a cosine here and then a 2. So think about those other 2 terms. And tell me, Rachel, which of these would be our best choice and why?
Could you go back to the problem I was writing down?
Sure.
See what it was.
So which of those 3 on the right that are equivalent to cosine of 2 theta makes sense in this case? Algebraically. You have to think ahead.
You probably do the top one.
Well, I think not.
Okay.
What do you think, Holden?
2 cosine squared theta minus 1.
I agree. Why?
Because it has the 2 and the theta 1 is fraction and the cosine and the other one is negative.
Okay, so I agree with your answer. I don't agree with your justification. Do you see how if I chose either of these 2, the first or the third, how many different trig functions would I have in the equation? I'd have 2, which makes my life more challenging. But if I choose the middle one, you see I would have only the cosine, and I could turn it into a quadratic. So again, thinking ahead, I think this would be the best choice. If I just randomly plug one of those in there, I'm gonna be chasing my tail. That's one of those where you throw your book against the wall, your mom comes to the door like, what's wrong? Just leave me alone, Mom. So think ahead, pick the right one. 2 cosine squared theta minus 1 is what I choose. And we're concerned about solutions on the unit circle, not all solutions, just solutions on the unit circle. Remember I told you there's 3 ways we can describe a solution. We can just pick any solution, which is rarely, if ever, used. We can list solutions on a given interval, or we can give all solutions. So it's normally on an interval or every solution. Those are the normal ways we describe solutions to a trig equation. All right, so we've got some simplifications to make here. We want to get it equal to 0. So 2 cosine squared theta, and I'm going to write it like this. And I'm going to subtract away 2, and I get 2 cosine squared theta minus cosine theta minus 3 equals 0. Now I'm going to do the U substitution method. U equals cosine theta. You guys are getting a ton of review on how to solve a quadratic here. So 2u squared minus u minus 3 equals 0 is the result. And we see that is indeed a quadratic relationship. And we can use those old quadratic solution techniques. John Jones probably taught you this. Algebra 2 early on. So let's see here. We need to find 2 numbers, m and n, such that their sum is that b value and their product is a times c. So I see that's -3 and +2. So I'm going to rewrite that middle term as -3u plus a +2u. Then I'll leave the other terms the same. Then I'll factor by parts. So I get u here, 2u minus 3. And when 2 values are relatively prime, in other words, they share no factors, I can always factor out a 1, which is what I'll do in this case. And we see that we have accomplished our task because we've got this common binomial factor. If in the solution of a quadratic by factoring, you don't encounter a common binomial factor here, you might as well go back because you've screwed up. So there has to be a binomial to factor out at this point. 2u minus 3 times u plus 1 equals 0. Now we can say 2u minus 3 equals 0, or u plus 1 equals 0, which means u equals 3/2, or u equals -1. Let's go back to our cosine, shall we? So remember we let u equal cosine theta. So we've got cosine theta equals 3/2, or cosine theta equals -1. Now, Rowdy, I can disconsider this on the left. Why?
Because it's greater than 1.
Indeed. You see how 3 over 2 is 1.5? It's impossible. So this is an answer that's outside of the range of the cosine. It's like saying 5 equals 6. It's nonsense. This one, on the other hand, does have a solution. So we're worried about on the unit circle. So Colin, tell me on the unit circle where the cosine as the x-coordinate is -1.
It's -1.
Indeed.
That is 180 degrees.
Good. How do we say that in radians?
Pi.
Indeed. So theta equals pi, and that's it. That's the only place on the unit circle where the cosine is -1.
So why again was that 1
Well, do you see, Rachel, how 3 over 2 is also 1.5?
Yeah.
And the range of the cosine, in other words, the things it can put out, is from -1 to 1. And see how this is not in that range? So this is an impossibility as a consequence. It might also help you to think about it graphically, Rachel. So if I were to graph the cosine, which I'll make a real rough graph here. You see how this is 1.5. When is the graph going to touch 1.5? Never. So that's also impossible. All right, so good question. Other questions? We put all this up here at once, just for a moment. The ultimate section of the ultimate chapter of the ultimate class. Some people, well, I would make the argument 7 part 4 is more challenging. But what's that?
What's chapter 7?
Chapter 7 is about conics, the conics of Apollonius. So again, the ancient Greeks had no time, or had time for the first time in human history to sit around and think about random crap. So Apollonius, which means little Apollo, Apollo was a god in the Greek pantheon, thought about, what if I had a double napped cone? In other words, a cone sitting on top of another cone with the pointy ends touching each other. And I sliced it at different angles. What shapes would result? Well, good question. But again, it had to do with the pathways traced out by stars in the sky. And in fact, conics describe those pathways perfectly. Thousands of years later, Johann Kepler, who was a patron, had a patron of Tycho Brahe. Tycho Brahe was an interesting character. He was sort of a lustful anarchist. He had lost his nose in a sword fight, replaced it with a golden nose. And he was sort of like the Bill Gates of his day, a rich guy that supported very intelligent people in their pursuits. Johann Kepler was extremely religious, so they went together like oil and water. But Tycho Brahe gave him money. Johann Kepler took it, and he studied the pathways of the stars. And he found several laws of motion for celestial bodies. And he found that they trace out ellipses, which are one of the conics found by Apollonius. And he thought, surely that must be a mistake, because an ellipse is less perfect than a circle. And surely the movement of celestial bodies must be perfect. But who's to say if an ellipse is less perfect than a circle? But he really thought he had screwed up. In fact, those laws of motion still hold. One of the few things scientifically from his time that are still considered absolutely true today. But yeah, that's chapter 7. That's coming up later. Hopefully we'll have fun with that. So this is a good one. Tangent 2 theta plus tangent theta equals 0. So if you look here, tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. So we'll just copy that to avoid the possibility of any transcription errors or lapses in memory. There we go. You see how we're not plagued by multiple choices in this case. There's only one tangent double angle identity. And so we know the right one to use is the only one. So I'm going to take this and replace it with this expression. So I get 2 tangent theta over 1 minus tangent squared theta plus tangent theta equals 0. So, and we're again concerned about the unit circle. If I were solving this problem on a quiz or a test, the first thing I would do is use my calculator, find the solutions, and then work backwards from those solutions. So there's 0 chance for an error. But, because we're just having fun here, we'll try to attack it algebraically exclusively. So let's see, what if I get this tangent over to the other side? I'm just trying to kind of get rid of this denominator. This denominator cramps my style. I don't like it. So you see how now I can multiply both sides by the denominator and get rid of it? Think ahead, like a chess game. Colin is one of only 2 children in the history of this school to beat me in a chess match. In my defense, I didn't take him seriously. Second game, I destroyed him.
Tried clowning in game 1.
Yeah, I thought I could just kind of beat him accidentally, but no.
Didn't work out.
No. But the key to chess is to think ahead of your opponent. And here again, the key is to think ahead of the equation. Where am I going? What am I going to do? So getting rid of that denominator, I think, is a good strategy. And here we've got 2 tangent theta. Although the potential to lose a solution is possible, if I ever divide away an expression that is a 0 or a factor, then I'm losing a 0. So whenever you divide by something, that possibility exists. You have to be careful and think about that as well. I don't think that's the case here. So distribute this, I get negative tangent theta plus tangent squared theta. All right, we're getting there.
When you become tangent cube theta,
Oh, thank you. Yeah, you're right. Yeah, it should be to the 3rd power. Thank you. All right, so let's get it equal to 0. The only way to get to solve an equation by factoring is to get it equal to 0 and then factor the other side. So we'll subtract away this 2 tangent theta, because that's the most efficient way to make that happen. This cancels out, we get 0. This is negative 3 tangent theta. Yes, plus tangent cube theta. And I've got a GCF over here. What's the greatest common factor on the right here, Macy? Indeed. So now we've got negative 3 plus tangent squared theta times tangent theta. So now I can use ZPP, the zero product property. One of my favorites, if you'll notice. Or tangent theta equals 0. And we're concerned again about solutions on the unit circle. Remember that I told you once or more that we are more calculator reliant with respect to the tangent. And if this were sine or cosine, I would start quizzing the class like, where's the sine here? What's the sine of what angle is equal to this? Harder to do that with the tangent because it's not explicit on the unit circle. It's implicit, built in. Have to divide the sine by the cosine. So we'll use the calculator here. Tangent inverse of square root of 3. And before I do this, I need to be in what kind of mode, Colby? Indeed. Which I'm not, so let's change that. So 60 degrees is a solution. Now, we have to remember the period of the tangent is pi, or 180 degrees. We're concerned about solutions on the unit circle. So from 0 to 2 pi. So we're missing a solution here. There's also a solution in Q3 that we have to find by saying 60 plus pi, or plus 180 degrees. So this is 60 degrees and then 240 degrees. Both solutions to this. This one we had to understand because of the period of the tangent function being 180 degrees. It's going to repeat itself. So the solution will be repeated on the unit circle at 240 degrees. So let's write this in radians because we like to talk about radians. 4 pi over 3. All right, and then the other one, tangent theta is 0 on the unit circle. So that's from 0. Yeah, let's do it that way. So that's from 0 to 2 pi. So for the zeros there.
0 pi and 2 pi.
Yeah, but if we look, we don't want to consider 2 pi. You see why? So just 0 and pi are the ones that make sense here. So our solutions are 0 pi, pi over 3, and 4 pi over 3. Now let's go back to our original strategy that I suggested, which was to use a calculator. We'll use it to check our answers, but if it were, if I were taking this as a test question, and my grade were on the line, I would have done this first and then worked backwards from the answers. If I wanted to, like make sure everything I did was right. But here I do the algebra first. It's kind of a risky strategy. Because again, you can lose a solution. You can come up with an extra solution that maybe doesn't work for whatever reason. Any kind of little sign error, a lot of calculation taking place here. And the error holding corrected, I probably would have found that on the next step because I've been like, what the heck, that doesn't make sense. But it's not certain. I could have went ahead and solved it and I would have lost this solution in that case. Okay, so anyway, let's graph this from 0 to 2 pi and see what happens. So if I want to solve this as it is, I can do that by setting the left side of the equation as y1 and the right side of the equation as y2. 2 times tangent x over 1 minus tangent x squared. I believe that's right. And our window will go from 0 to 2 pi, so that's good. Probably need a little more y. Let's go negative 10 to 10. That way we've got a pretty good view of what's going on. Oh, I'm in degree mode. So if your graph ever looks weird, change it to radian mode. Definitely a weird graph here, bros. Wow, he's thinking hard about this. There we go. As I said, for this section, you will be switching up your modes frequently. Wow. Really doesn't like that second expression. Yeah, so this one this calculator isn't a good interface for a graphical solution. I'd probably have to look at Wolfram. Maybe I don't have quite enough Y, or maybe the graphs are so close it looks like the same graph or something. I don't know. In any event, graphing is usually a good strategy, not in this case for whatever reason. We want to know what thetas make this true, so this is an algebraic mechanism to arrive at that answer. Okay, so now power reducing identities, ladies and gentlemen. These are probably the ones I like the least because they create a situation that's just an absolute mess. And guess what? Every year, so mathematicians are creatures of habit. Just think about what would make you inclined towards mathematics as a field of study. You're a habitual algorithm following person. So every year, first question on the statewide dual credit test, which you'll all take for college credit for this course, is a power reduction identity. Every year. And it is a mess. Yeah, so every year they use one of these for the very first question. And I'm just like, whew. But anyway, sine squared theta is 1 minus cosine of 2 theta over 2. Cosine of 2 theta is 1 plus cosine 2 theta over 2. And tangent squared theta is 1 minus cosine 2 theta over 1 plus cosine 2 theta. So as you can see, we're not only going to be using the power reduction, we're also going to be using some double angles here to simplify the result. All right, so this task is to rewrite cosecant to the 4th power of theta in terms of cosines of multiple angles with no power greater than 1. So we're not trying to solve anything. There's no equal sign here. This is an expression, and we want to rewrite it in such a way that it has cosines with nothing to a power greater than 1. So another way to think about this is 1 over sine to the 4th power of theta. Everybody with me so far? All right, because cosecant is 1 over the sine. And another way to think about that is 1 over sine squared theta times sine squared theta. The reason why I do that, Rowdy, you see any 4th powers here? Oh, they're all squared, aren't they? So you see why this is an advantageous choice. All right. So 1 over, and then I'm going to plug in that identity from the previous page for sine squared theta. So in both cases, both signs down here in the denominator, we're going to replace with 1 minus cosine 2 theta over 2. So that's an application of the power reduction identity. You might think, hooray, we're done. All single powers. No. If we multiply this out, we're still going to have something squared. And this is almost exactly how that one on the statewide dual credit test works out. So if I multiply here, these have the same numerator, of course. And then divided by 4. 2 times 2 is 4. So remember that to divide by a fraction is keep, change, flip. So we can rewrite that like this. Now let's square that trigonometric expression in the denominator. So that's 4 over. Remember that a minus b squared equals a squared minus 2ab plus b squared. So we'll use that shortcut. So that's going to be a squared minus 2ab. That's 1 times cosine or 2 theta, or just cosine 2 theta. And then here's where the problem comes in, plus b squared. So cosine of 2 theta squared. This is our problem. We still have an expression that is to the 2nd power. We have to address that. And we'll use another identity to make that happen from the previous page. This time we're going to use the cosine power reducing identity. So we're going to take this term and replace it with that expression. A problem you run into here, and there's a multiple choice test question about this as well, is simplification. So you can get the right answer, but it's difficult to understand it's the same if you don't simplify in the same way. Complex fractions, and I have to be careful here because my argument doubles. You see, this argument is theta, and this argument is 2 theta. So here we're starting out with 2 theta. So what do you think our argument becomes, Jesse? So in the identity, the argument of theta becomes 2 theta. Here we start out with 2 theta. So what should this argument be?
1 plus cosine 2 theta over 2.
No, because do you see what I'm talking about with the argument here, Jesse? You see how in this identity, the argument is just theta. But here it's 2 theta.
Oh, yeah, you need an identity.
Say that again.
You had an identity.
Well, no, the same identity will apply. We just have to extrapolate. So if theta becomes 2 theta, then 2 theta becomes, so it's just like a machine. It just doubles what you put into it. So if it doubles $1, we get $2. If it doubles $2, what do we get? Okay, you're missing the point, Jesse. This mechanism doubles the input. Here we start with 2. What is double 2? So this is also a point where a lot of people would miss this. So cosine of 4 theta for this. So a lot of people could get to this point, but then they wouldn't quite get to the answer because as I recall, the multiple choice answer does not include a complex fraction because that's considered unsimplified. So do you see how I could multiply top and bottom by 2 and get rid of this? Yeah. So if I multiply the numerator by 2, it becomes 8. If I multiply the denominator by 2, I get this. And now I've got one more simplification to make, which is 8 over 2 plus 1 is 3. And now we have accomplished our objective. Look how innocuous that little expression looked at first. And then look what he became.
What's that last part of the answer again?
8 over 3 minus 4 cosine 2 theta plus cosine of 4 theta. Question, Macy? Sure. Other questions? All right. Hardest problem in the book, I'm going to go hit my jewel. I'm just kidding. Macy wouldn't do that. Heard a funny story that somebody wrote Jewel Gang on the jewel detector in the bathroom. Wow. Thug life. Moving on. So we're going to solve an equation using a power reduction identity. We could also solve this with the Pythagorean identity and then the double angle identity, but instead we're going to use a power reducing identity. So the first problem, or the first part we need to attack is this sine squared theta. So let's talk about that first. Remember that is 1 minus cosine 2 theta over 2. And then plus cosine 2 theta minus cosine theta equals 0. So I need to combine these two terms before I apply a double angle identity. I will eventually have to do that. So we're trying to solve this equation, and they don't give us an interval, so we need to give all solutions. That should be the default. So I can write this as 1 over 2 minus cosine 2 theta over 2 plus cosine 2 theta minus cosine theta equals 0. Okay, so these two terms are like trigonometric terms. They've got the same trig function, same argument. This is minus 1/2, and this is plus a whole. So do you see how the result would be positive 1/2? So if I combine these two trig terms, I'm going to get 1/2 and then plus cosine 2 theta over 2. So that is the sum of these two. So this is minus 1/2 plus a whole, positive 1/2 is what remains. So I don't like all these denominators. Just to make my life easier, I'm going to multiply through by 2 at this point, both sides times 2, to give me 1 plus cosine 2 theta minus 2 cosine theta equals 0. So the left side times 2, 2 times 1/2 is 1. 2 times this value over 2 is just that value. And then 2 times minus cosine theta is minus 2 cosine theta. 2 times 0, in fact, anything times 0 is 0. So I performed the algebraic step of multiplying both sides by 2 to get from here to here. Now we're ready to apply a double angle identity. Now remember we had 3 for cosine. Which one is our best choice here? Grace. Remember we got some cosines in that equation. Which of these would make the most sense?
What was the middle one?
Good choice. That would result in only one trig function with one argument. So that's the only one, in fact, that we could solve easily. So we'll utilize that.
So how did exactly you know which one fit?
Because like a chess player, I'm thinking ahead. And I'll explain that more thoroughly here in just a second. So like a chess player, I'm thinking ahead, and I see that if I plug this one in, Rachel, you see how the result is just going to have cosine theta? It's not going to have sine theta, tangent theta. It's not going to have 2 different trig functions, in other words. And I know that to attack it with our conventional algebraic strategies, I need that to be the case. So you have to be able to think ahead and know where you're going. One way to do that is to just mindlessly pick one, plug it in, and see what happens. Keep doing that until you get something that's solvable. Now, that's not the ideal strategy. It's inefficient, but it is a strategy. But in this case, Grace correctly guided us towards the right one. So 1 plus 2 cosine squared theta minus 1 minus 2 cosine theta equals 0. So you see how this is something we can solve using the techniques we've talked about so far. Additive inverse here, 1 and negative 1. So my result is 2 cosine squared theta minus 2 cosine theta equals 0. Clay, what's my GCF here?
2 cosine.
Very good. So 2 cosine theta times cosine theta minus 1 equals 0. I can divide away that 2 if I want, but I'll just do it like this. So 2 cosine theta equals 0, that means cosine equals 0. And if cosine theta minus 1 equals 0, that means cosine theta equals 1. So we're worried about where this is true. And again, we weren't given an interval. They didn't say on the unit circle. So we're going to give them all solutions, every possible solution. So where is the cosine 0? So if we were to graph it, that would indeed be at 90 degrees. But also, do you see at 270 degrees? Or negative 90 degrees? So let's think about that in terms of radians. So that's pi over 2, and then 3 pi over 2. And what is the period of the cosine function, Caitlin?
The 2 pi?
Very good. 2 pi. So plus 2 pi n. But there's an easier way to write both of these. So you see how this is 90, and then 90 plus 360, and then 90 plus 720, and so on. And this is 270 plus 360, and so on and so on. So, but you see how these are exactly pi units apart, or 180 degrees apart, which is pi. So another way to say both of these at once is pi over 2 plus n pi. And there's a multiple choice question where that simplification is made on the test. And you'll miss it if you don't understand how I got from here to here. Let me write that a little more clearly, because that's kind of a mess. So together, those can be described with the single expression pi over 2 plus n pi. All right, now let's get over here to cosine theta equals 1. So cosine theta is positive 1 at 0 plus 2 pi n. And that's it. So 0 plus 2 pi n. 0, 2 pi, 4 pi, 6 pi. 0, negative 2 pi, negative 4 pi, and so on. So our solutions are here and here. We go to full page here. Stop me if you guys have a question, thought, comment. A lot of questions, some philosophical thoughts. Vice presidential debate last night. The fly that landed on Mike Pence's head was the real star of that show. He was there for a long time. That's a lot of hairspray, boys. You get stuck in that quagmire, you're not getting out for a minute. All right, so let's talk about something called a half-angle identity. And in this case, you've got 1 for the sine and cosine, 3 for the tangent. Notice there's a lot of radicals here. This can get kind of messy. But just like the earlier identities we discussed, this extends our knowledge of exact values for the trig ratios of certain angles that weren't on the original unit circle. You see how now I can do half of any of the unit circle angles and know it exactly. So this further extends our knowledge of exact values for trig ratios. So on that sheet, you don't have to write it down, but know how to find it, know what it is. 22.5, see how that's half of a value that is on the unit circle. So sine of 22.5 is also the sine of 45 over 2. See how that's true? And remember that the sine of theta over 2, this is from that previous page, is plus or minus the square root of 1 minus cosine theta over 2. And we'll know it's positive or negative because of the quadrant location. So this is in Q1, meaning which of these two is true, Bristol?
Plus.
Very good. So I know it's positive because of Q1. So extrapolating from that, I know this is going to be positive 1 minus cosine 45 degrees over 2. Okay, so this is going to be square root of 1 minus, haven't got to do this much today. Riley, what is cosine of 45 degrees? Excellent. I think some of you have taken to having your unit circle right there in front of you. But you have quelled my rage for a brief time. I was pretty upset when so many people missed those questions earlier in the week. Okay. So some simplifications, complex fractions again, we don't like them. So let's fix that complex fraction. Multiply top and bottom by 2 here. So the numerator times 2 is 2 minus square root of 2. The denominator times 2 is 4. A fraction or a root within a root is probably novel to you. In other words, you haven't seen it very much. But we've got this equivalent expression, which I can also reduce further. A lot of twos, boys. But again, with a multiple choice answer, you have to know how to make that simplification because it won't show up like this. It'll look like this in that answer set. Let's test our result. We need to be in degree mode here. Sine 22.5. And then the square root of 2 minus the square root of 2. Close the inner root, close the outer root, divide the result by 2, and you see we get the same value. Yes. Satisfying, isn't it? Okay, questions about anything? Okay, so we get into some funky algebra at this point, but let's solve an equation using a half-angle identity. So again, full disclosure, we're worried about solutions on the unit circle. The first thing I would do is graph this and look for intersections. So I would probably subtract this over, get this side equal to 0, graph the resulting expression over here, look for its x-intercepts, and then work backwards. But because we're just having fun exploring these problems, we'll attack it algebraically first. So I see I've got some a couple half angles, but this is squared. So another way to think about this is like that. The unusual position of the superscript can prevent you from understanding that that's an equivalent expression. So we need one for the sine and one for the cosine. Let's steal these two. Only when you don't want it to does it do that. Okay. So we'll rewrite the sine of x over 2 as this expression, and the cosine of x over 2 is that expression. So we've got plus or minus, but you see how it doesn't matter if we're squaring it anyway? So we'll just consider it positive. So we're squaring both sides anyway. Doesn't matter if we make it positive or negative. The result will be positive all the same. We will have to be conscious of potential for extraneous solutions, as always when we square both sides. All right, so the square and the root will cancel out. If I multiply both sides by 2, add cosine to both sides here. I get 1 equals 1 plus 2 cosine theta. Subtract 1. 0 equals 2 cosine theta, which means cosine theta equals 0. And we're worried about the unit circle this time, I believe. Yep. So on the unit circle, where's the cosine 0? Mackenzie.
I'm sorry.
So on the unit circle, where's the cosine of theta 0? For what theta?
One.
So not quite. Think about the angles we would plug in. 1 wouldn't be an angle. Where would the x coordinate be 0 on the unit circle?
At 0 degrees.
That's where the y coordinate is 0, but the x coordinate is 1 at that point. So where is the x coordinate 0? Where are you touching the y-axis? Okay. Unit circle. This is the y-axis. You tell me, stop me when I touch it, Mackenzie. What angle is that?
90.
4 in radians.
2 pi over 3.
Okay, so you probably need to download a unit circle because that's not correct.
Okay, I have one right in front of me. I guess I just have it wrong.
Yeah, this is pi over 2. 90 degrees or pi over 2. And then if I go around, yeah, I'm touching it again here.
Mm-hmm.
What's this angle?
270.
In radians?
4 pi over 3.
Okay, also incorrect. So that unit circle is not reliable. 3 pi over 2 is what that one is. So clearly you were rushed when you wrote that down and you messed up a few. So consult Wikipedia and correct all those on your unit circle, or you're going to miss a lot of questions on the test, okay? Wikipedia is absolutely reliable in 99% of cases, despite what your English teacher tells you. Wisdom of the crowd and so on. Any source should be suspect to you as little scientists. Trust nothing. Falsifiable, verifiable, experimentation. That's it. That's the only thing you can count in the universe. But you have to depend on experts in other fields to a degree. You can't know everything, right? Like if I wanted to know something about geology, I'm not going to study for 4 years and get a geology degree. I'm going to go to Wikipedia and go look down at the sources at the bottom. You know what I'm talking about? Click on those, see the actual scientific papers that information was drawn from, and then I'm going to extrapolate from their expertise what I need to know. So Wikipedia is reliable in the case of unit circle especially. Make sure and correct any mistakes you have on yours, because if you've got the wrong angles and radians, and you might as well be reading a children's book. It will be of no use to you. All right, so product to sum identities. A lot of times I don't go all the way to example 7 in the section because your attention is finite. Welcome in. And, I know I'm challenging your attention span with this class anyway. It's not the most compelling sometimes. And 7 examples is just sometimes too much. But in this case, we have to because it's on the test. In fact, I think 4 out of these 7 examples have an exact analog on the test. So let's do it. Use an identity to write a product as a sum or a difference. So what algebraic operation, and those are addition, subtraction, multiplication, and division, which of those is taking place between these two terms, Rowdy?
Multiplication.
So we've got a product, and we want to rewrite that as a sum or a difference. So we've got cosine of something times cosine of something. So if I look back at my list of product to sum identities, I see that matches this one. Cosine times cosine. So let's use that one to rewrite it as a sum. And this is actually a simple question. This one's basically a gimme. Come on now. What have you done to me? Okay. Sometimes I think this software is designed to elicit the maximum number of clicks to accomplish a single task. Anyway, here we are. So cosine times cosine is equal to this. So cosine of 6x times cosine of 3x equals 1/2. And then cosine, and this is like alpha, and this is like beta. So this is 6x minus 3x plus cosine 6x plus 3x. Simplify. That's it. So you see why you shouldn't miss that one. That one should be a gimme. And then there's one more potential situation where you go the other way. So they might give you something that looks like this and ask you to rewrite it as a product. You see how you would just apply that identity in reverse. I think the test one goes this way. So this is the other way. You got a sum here, a product here. Just the functional inverse of what you just saw. So use a product to sum. Find the exact value of the following. So what they want you to do here is think about what two angles on the unit circle would have this as their sum and this as their difference. 225 and 30, I believe. So I think this is like alpha plus beta. And then over here, this is 225 minus 30. So you see how that's another way to say the same thing? So if we think over here with our identities, and we can use these sum to products, I guess. Sin alpha, sin beta. Well, for me, it's easier to just use this. So I see that this is a cosine alpha plus beta plus cosine of alpha minus beta. And I could match that up. Cosine alpha plus beta. Yeah, okay, so that's the same as this, we just got them backwards. So it'd be easiest for me to apply this identity in this case. So this expression that I'm concerned about matches up to this. If I multiply both sides by 2 here, do you see how that would equal 2 cosine alpha, cosine beta? And just multiplying both sides by 2 quickly gives us this. And I'm going to commute and write this one first because that's the way I wrote it here. So I get that, and I can use alpha is 225. And beta is 30. So this is 2 times the cosine of 225 times the cosine of 30 equal to that expression we're concerned about. So what is the cosine of 225, Colby?
Negative radical 2 over 2.
Should be able to do that mentally, sir.
Sorry.
It's all right. You guys got it easy with this test and online nonsense.
I know the first 2 quadrants, but after that it's a little rough.
Yeah. Well, just remember everything's negative in symmetry in Q3. And y negative, x positive in Q4. Caitlin, what is this cosine of 30? Excellent. So if I multiply through here, 2, see these 2's will cancel. And I get negative root 6 over 2. Let's test our solution, shall we? Negative root 6 over 2. So Are we in degree mode? Yes. Cosine 255 plus cosine of 195. Is this value, and if I do negative square root 6 divided by 2, yes, very satisfying. All right, so that's it. Chapter 5 is open. At least as far as the new material goes. You will have review tomorrow with the sub. Test over the weekend to be completed at your leisure. And then when I see you again, we will begin chapter 6.
So you said that this one was hard. I thought the last one was harder than this one.
I think algebraically, I think you're kind of numb at this point, Rowdy. But if you look at problems like this or problems like this,
Pretty much.
this one especially.
No, I feel like I just understood it more. I'm not saying it's like easier necessarily, but I understood this one more.
Well, I'm glad. I do my best, you know.
I think 5-2 is more.
Yeah, I think probably you're onto something there because you have to. The target is not as clear.
5-2 is just so 15, 5 now.
All right, so let me give you a brief assignment, ladies and gents, which I don't have on here, so I'll have to consult my. Well, I've got it on Google Classroom, I think. Maybe not. I'll consult my assignment list. Five. Oh yeah.
We don't have that much left.
We don't, especially when you consider only do 3 sections each from chapters 8, 9, and 10. We are well over halfway through the material we'll cover. Well over. So your task is page 352, 2, 4, 6, 10, 12, 15, and 18. Turn my video off here.